In this lab, I used supplied data of the location of a star orbiting a black hole to estimate the net force on the star, and from this I estimated the mass of the black hole. The data that I was given consisted of the mass of the star and the location of the star every 86,400 seconds. I used the observed position of the star to estimate the velocity of the star, and from this to find an estimate of dp/dt, the change in momentum versus time. dp/dt has a component parallel to the direction of motion and a component perpendicular to the direction of motion. I used my estimates of the momentum that I made from the observed data to find an estimate for the component of dp/dt parallel to the direction of motion, and I used this estimate along with my estimate for dp/dt to find an estimate for the component of dp/dt perpendicular to the direction of motion. I then used Newton's second law. Newton's second law says that the change in momentum of the star is due to an interaction of the star with something in its surroundings, and that the net force acting on the star is equal to dp/dt. The net force acting on the star can be broken into two components, the component parallel to the direction of motion and the component perpendicular to the direction of motion, corresponding to the two components of dp/dt. Here's the code that I used to do the computations. I inputted the mass of the star and the time interval between each of the observed locations, and then I used the locations to find an estimate for the velocity vector at each position. This I used to estimate the momentum at each location, which I used to find an estimate for dp/dt. Newton's second law says that this vector will equal the net force acting on the star. I changed the arrow scale so that when we run this we can see the motion, and when we run it we see that the net force, which is the yellow vector, is pointing in the direction of this black dot here, which I placed at the origin. This is consistent with the assumption that we were asked to make, that is, the assumption that the net force on the star is due to the gravitational force of a black hole located at the origin on the star. Assuming that the net force on the star is due to an interaction with a black hole located at the origin, I used Newton's law of universal gravitation to conclude that the magnitude of the net force should be equal to the universal gravitation constant g times the mass of the star times the unknown mass of the black hole divided by the square of the distance between the star and the black hole. Since the black hole is located at the origin, the distance between the star and the black hole will be equal to the magnitude of the position vector of the star. From this, I found the expression here for the unknown mass of the black hole in terms of the magnitude of the net force and the observed data, the distance between the star and the origin, and the mass of the star. I used Python to do the computations. If the assumption is correct, then this expression here should be constant throughout the star's motion. I ran this and printed this, the result of this computation for each time position. I've already done it because it took a little while, and we see that it is indeed nearly constant throughout the star's entire motion. And so I can use this to estimate the mass of the black hole and to 3 significant digits, which was how many significant digits we were given of the mass of the star. We see that the mass of the black hole is 1.98 times 10 to the 31st power kilograms. Since my estimate for the mass of the black hole came entirely from the observations made of the star's location over time, if the observed data remained the same, I would get the same estimate for the mass of the black hole, so I would be unable to tell the difference between two different black holes located at the origin based only on the observations of the star's motion.